Let's take a look at our second comparison test called the limit comparison test. But before we do that, let's discuss why we need another comparison test, because we already have the direct comparison test. But in the direct comparison test, we do have to make the inequality work. We got to make the inequality be the right set, the right order in order for it to work. So let's consider something for an example first. So let's say we're taking the series that we have here on the board. We've got 1 over k squared minus 2 from k equals 3 to infinity. And we can see pretty clearly, as we were talking about on the last series, we got to figure out what we want to compare it to. So we look at the series of terms, the terms in the series, and we kind of think about, well, what does that look like? And clearly that negative 2 is going to get dominated by the k squared. And so the series we would want to compare it to is 1 over k squared. And we know that 1 over k squared is going to converge by p series, p equals 2, which is greater than 1. So we do know that that's a converging series that we want to compare it to, but we have to be able to set up the inequality. So let's think about it. If we try to set this inequality up, and I'm just going to come over here on the side, if we try to set this inequality up, we know that k squared minus 2 is always less than k squared. So when we flip this, we get 1 over k squared minus 2 when we reciprocate the terms would have to be greater than 1 over k squared, and they are positive terms. I'm going to rewrite it this way. So 1 over k squared is smaller than 1 over k squared minus 2. Now, that's the problem right there, because the series that we know converges is smaller than, less than the series we're comparing it to. And so that leaves me with a big question mark. When you have a series that is converging, if that is smaller than some other series, it tells us nothing about that other series. That other series could converge, but it might diverge. We just don't know. It's bigger than the converging series. It's not being, it's not less than where it's being trapped underneath the converging series, which would force it to also have convergence. In this case, we just don't know anything. It's inconclusive at this point. So it's inconclusive, but we know inconclusive. This inequality doesn't tell us anything. It would be inconclusive in terms of the convergence or divergence of 1 over k squared minus 2. But we know, we're just like, oh man, we're so convinced this has to behave like this. So is there another way that I can compare it? And the answer is yes. We can use what is called the limit comparison test. The limit comparison test is pretty cool actually, because what the limit comparison test does is it lets me compare tests without having to compare two different series that we know are similar or should behave like each other. It lets me compare them in such a way that doesn't require me to build an inequality. So let's talk about this. The limit comparison test, we'll abbreviate it LCT for short, limit comparison test, says that as long as we have two series, so the form of the series that we're looking at, we've got two different series, A sub k and B sub k, with positive terms. The terms do have to be positive. And what we do is we take the limit of the ratio of those terms, so A sub k over B sub k as k goes to infinity. If that equals L, which is greater than 0 and finite, so it's got to be greater than 0 and it has to be finite, so somewhere between 0 and infinity, a real number, then both the series converge or both the series diverge. So we'll do the same thing we did with the direct comparison test. We'll identify a series we want to compare it to, and then rather than building an inequality, we'll take a limit and see if that limit becomes a finite number. If that is true, I should say a positive finite number. If that is true, then both the series are converging or both are diverging. So if the one we're comparing it to is diverging, then the series we're looking at would also diverge. If the series that we're comparing it to converges, then our series would also converge. Now, a couple of things. Given a series, you do need to find a series that you can take the limit of the ratio of the series, and then we tend to use, again, geometric or p-series because we are still comparing just in a different way. So we'll tend to use geometric and p-series because those ones are easy to identify if they converge or diverge. And if L equals 0, then the limit comparison test is inconclusive, except in a special case. There's one other special case I want to talk about too. And so I will add those here at the end. So for the limit comparison test, let's try to get it all on the screen at the same time if we can. So for the limit comparison test, there are these two special cases at the bottom. And these special cases I didn't put on your sheet, but if you wanted to add them into your notes, this would be a good time to do that. If when we take that limit, if we get L and it is 0, now this is a big and the series that we're looking at that's in the denominator is converging, then the series that we did in the ratio on the numerator will also converge. If on the other hand, that limit that we happen to be looking at, a sub k over b sub k equals L, and that L is infinity. So these are two special cases, and the denominator series, the series in the denominator of the ratio we looked at, if that series is diverging, then a sub k will diverge as well. So if we take the series that we're comparing to and we put it into the denominator, then if in that special case we don't get a finite number greater than 0, but we happen to get 0 in that special case where b sub k is converging, then a sub k will converge. And if we happen to have a b sub k that's diverging and we get infinity, then a sub k will also diverge. So that's what those two special cases say, and we can utilize those as well in this test. So again, some quick notes about using comparison tests. The first step when we're using our comparison test is to actually find that series that we want to compare to. And again, this is where we would want to probably think about our p-series, our geometric series, or any other known series that we know. Then we will apply the direct comparison test. So this is what we were doing on the previous video. If we can easily build the inequality, then we can use the direct comparison test. But on this video, we're going to talk about the limit comparison test, where we will take the limit of the ratio of the two series, and we will consider what happens as k goes to infinity. So we're going to consider what happens as k goes to infinity, and we'll take a limit, and then they will either, if it is a finite positive number, then we will have either both convergence or both divergence. So this is useful if we cannot build a direct inequality. Okay, so that can be a use. The limit comparison test is useful if we want to use comparison, but we can't build the direct comparison. Okay, so back to that example that motivated the use of this test. So again, we are just picking up right where we left off. This is the series from k equals 3 to infinity of 1 over k squared minus 2. We want to compare to this, but we already showed earlier in this video that it was going to be impossible to set up the inequality in the right way because we know that this series is converging. So what I'm going to do instead is I'm going to take the limit as k is approaching infinity, and I'm going to take a ratio here. So I'm going to take 1 over k squared. Actually, it doesn't matter unless we're going to use one of those special cases, which of the series we put on top. So I just started with 1 over k squared. I'm going to put 1 over k squared minus 2 on the bottom. This is going to become the limit as k is approaching infinity. That's just a compound fraction, so I'm just going to redo it. K squared, 1 over k squared times k squared minus 2 over 1. And then, of course, I'm going to multiply the tops and the bottoms together. It's not going to do anything. So this is going to become the limit as k is approaching infinity of k squared minus 2 over k squared. Since I want to take the limit, this is the limit as k is approaching infinity. We're going to get 1 minus 2 over k squared. We're going to take the limit. This guy's going to go to 0. And we're going to get 1. So we get 1, which is definitely a finite number that is greater than 0. So that's definitely finite, and should have put the greater than 0 first. Finite and greater than 0. And so since that's finite, that's what our L value is. We can think of that also as our L value. That's what our L value is. And since it's finite, what that means by the limit comparison test, so therefore by the limit comparison test, the series that I'm looking at, 1 over k squared minus 2 from k equals 3 to infinity, has to converge since the series I compared it to, 1 over k squared from k equals 3 to infinity, was converging by p series. And that's how we can apply the limit comparison test. So again, start off the same way as with the comparison test, determine what we want to compare to and if it's converging or diverging. And then if we can't build the direct inequality, we go right into our limit comparison test. So let's look at another one. Let's take a look at this guy. So on this guy, I'm looking at this and I'm noticing in the numerator and the denominator those two terms that are going to dominate this series, the, the terms. So we're going to compare it to the series of 2 to the k over 3 to the k from k equals 1 to infinity. But of course, that's just 2/3 to the k from k equals 1 to infinity, which is a geometric series where r equals 2/3, which of course is less than 1. So it also converges by, in this case, not p-series, but geometric series. All right, so we want to compare it to a converging series, converging geometric series, but rather than setting up the inequality, because I say I'm adding one in both the top and the bottom, so the inequality is going to be difficult unless I split it up into two different series. And so I'm going to just go right into the limit comparison test. So I'm going to take the limit as k is approaching infinity. I'm going to go ahead and take my 1 plus 2 to the k over 1 plus 3 to the k over 2 to the k divided by 3 to the k, which of course is just the limit as k is approaching infinity, is 1 plus 2 to the k over 1 plus 3 to the k, and we've got 3 to the k, woo, 3 to the k on the top, multiply by the reciprocal of the denominator, 3 to the k on the top, 2 to the k on the bottom. And I'm going to go ahead and multiply each of those terms by 3 to the k and apply some rules of bases and exponential. So we've got the limit as k is approaching infinity. We've got 3 to the k plus 2 to the k times 3 to the k becomes 6 to the k. On the bottom, we've got 2 to the k plus, again, 3 to the k times 2 to the k is 6 to the k. And of course, this is infinity over infinity if I take a look at this. So I'm going to use some algebra to get this guy simplified some more. I'm going to actually multiply the top and the bottom by that highest term on the bottom. So note what I'm doing here is divide by the highest term in the denominator. That goes back a ways into limit theory from Calc 1. So I'm going to do that. Take the limit as k is approaching infinity. When I do that, I get 1 over 2 to the k. Now I'm going to distribute it, again, using my rules of exponential functions. So I get 3 to the k over 6 to the k, which of course becomes just 1 over 2 to the k plus 1. And then I get 1 over 3 to the k plus 1. And now I let k go to infinity, and these guys are going to approach 0, each of those terms. And so this becomes 1, which is L, which is clearly, again, greater than 0 and finite. Therefore, by the limit comparison test, again, LCT, the series I was looking at, which looked almost, it wasn't a geometric series, but it looked so close to it that we wanted to be able to compare. So we can with the limit comparison test from k equals 1 to infinity, converges since the series 2/3 to the k, the one I compared it to, from k equals 1 to infinity, converges by geometric series. R equals 2/3. So this guy looks a lot like a geometric series and in fact behaves like a geometric series and does converge. All right, let's just do one more. We have 2 with convergence. Let's see what happens with this guy. So on this guy, same thing. I'm going to try to figure out what it is that I want to compare it to. So compare to. What should I compare to? Well, I've got the series from k equals 2 to infinity. I've got 4k squared, so that's the dominating term on the top. And in the bottom, I have a cube root, but under the cube root, I have the highest power on the denominator is k to the 7th. So I'm looking at this and I'm thinking, you know what? I want to compare it to a series where the highest power on the top is k squared, and the highest power on the bottom is the cube root of k to the 7th, taking those highest powers of the top and the bottom. And then just using some rules of exponents, let's see, what does this turn into? This is k squared, and then of course the cube root of k to the 7th is k to the 7/3. And so when I subtract exponents and drop my negative exponent to the bottom, this is going to become 1 over k to the 1/3, or the cube root of k. And so this is p series, definitely p series, where my p is 1/3. So this is p series where p equals 1/3, which of course is less than 1, so this will diverge by p series. Okay, so this series that I'm looking at, essentially if we think about just what it's going to boil down to as the k's approach infinity, we're going to have the numerator being dominated by a k squared and the denominator being dominated by a cube root of k to the 7th, or k to the 7/3. And of course that would boil down to 1 over k to the 1/3 in the denominator. So that diverges by the p series. But again, I see I'm adding a k and adding a k cubed in the bottom. That's going to be difficult to set up the inequality. So I'm going to go to the limit comparison test again. And I'm going to say, okay, let's take the limit as k is approaching infinity. Let's take our 4k squared plus k over the cube root of k to the 7th plus k cubed, and let's divide that by 1 over k to the 1/3. Well, just like on the previous ones, I'm going to multiply by the reciprocal. So we'll multiply by the reciprocal. I'll go ahead and carry that throughout the numerator. So this is the limit as k is approaching infinity. I get 4k. Let's see, k to the 1/3 times k squared. We're going to get k to the 7/3 plus k. That's to the first, so that becomes to the 4/3. And in the bottom, I've got the cube root of k to the 7th plus k cubed. So, that's kind of a messy limit. In its current form, it's infinity over infinity if I tried to plug in infinity right now. And so again, I'm going to do the same thing we did on the last one. I'm going to divide top and bottom by that highest power in the denominator. It's a nice little trick for taking limits at infinity from Calc 1. So by the highest power in the denominator. And so when I look at the denominator, I have to kind of think about the fact that it's obviously k to the 7th is the highest power on k, but it's under a cube root. So the highest power in the denominator is actually k to the 7/3. So it's 1 over k to the 7/3. So I'm going to multiply top and bottom by that. It's just a fancy one. And I'm still taking the limit. I haven't done it yet. I want to get this simplified. And I'm going to end up with 4 plus 1 over k, because I get k to the 4/3 over k to the 7/3 in the top. In the bottom, remember that k to the 7/3 is the same as the cube root of k to the 7th, so that can come right underneath that cube root, and we get 1 plus 1 over k to the 4th, and this is a cube root. Left my index off. Now, each of these is going to approach 0. And so as k goes to infinity, this is going to become 4 over 1, the cube root of 1, which is just 4. That is my L value, and that is clearly greater than 0 and finite. And so what the limit comparison test says is that both series either converge or they both diverge. And since the series we're comparing it to is diverging, we can say that our series must also diverge, because in the limit comparison test, we got back a value of L that was greater than 0 and finite. So we can say by the limit comparison test, the series 4k squared plus k over the cube root of k to the 7th plus k cubed from k equals 2 to infinity converges, not converges, diverges. Our other two were converging, other two examples, but this guy is diverging because 1 over k to the 1/3 from k equals 2 to infinity diverges by p series. p equal to 1/3, which is less than 1. And so both series are either going to diverge or converge. In this case, the series we were comparing it to is diverging. So our series will also diverge through the limit comparison test. Okay, so this is a useful test if we're trying to compare, we want to compare, but we can't quite build the direct inequality like we were in the examples from the direct comparison test. If we can build the direct inequality, we can go that route. But if not, we can still use a comparison test. We just call it limit comparison test and take the limit to determine.